In the previous example, we found an analytical solution, and we also found a numerical solution. In this case, the analytical solution was easy to find. We had a single first-order linear ODE that we already knew the solution to. However, as we increase the number of coupled equations in a model, typically the difficulty also increases. This is true whether we're solving an algebraic model, an ODE model, or a PDE model. Even for algebraic models, if we have an extremely large number of equations, there are so many calculations to perform that the model essentially becomes impossible to solve. The impossible region is represented by the gray area on this plot. For linear sets of ODEs, we can find solutions, but again, as the number of equations increases, the difficulty of finding those solutions also increases. And for PDE models, only the simplest models even have analytical solutions. Many PDE models are essentially impossible to find analytical solutions to. And if our model equations are nonlinear instead of linear, then these curves shift up on the plot shown here, meaning that the solutions become even more difficult to find. And even a modest number of nonlinear algebraic equations can be impossible to solve. This is not very encouraging. This is a course on mathematical modeling and on model solution methods. And what I'm showing you here is that many of the types of models that you might encounter as a chemical and biological engineer are essentially impossible for you to solve. In fact, that's one of the reasons why you need this course. Throughout this course, we will learn modeling techniques that enable you to do the impossible. Some of the techniques that we will learn will enable you to make an impossible solution merely very difficult, and a very difficult solution moderate or easy, or even trivial. The techniques that we will use do things like converting PDE models to ODE models, and converting ODE models to algebraic models to make them easier, or converting nonlinear models to linear models, again, to make them easier. Or perhaps reducing the number of coupled equations, or reducing the number of variables. While this figure shows you the relative difficulty of finding analytical solutions, generally finding numerical solutions is easier than finding analytical solutions. Numerical solutions might be one step easier on the y-axis here than finding analytical solutions. So to summarize what we've talked about from Chapter 1 of the notes, quantities include 4 types: numbers, parameters, constants of nature, and variables. The variables are divided into 2 types. Some are dependent variables and some are independent variables. Numbers and constants of nature are not things that you can change or select. The inputs to a model are the parameters and the independent variables. And the outputs of a model are the dependent variables. All quantities have a magnitude on a scale and dimensions that should be indicated by the units. They can be either extensive or intensive. Quantities can be scalar, vector, or matrix quantities, and they can also be tensors, and we talked about some of the properties of these. The structure of the model equations can suggest what form the solution will take. Some models are algebraic, others are composed of ODE equations, and other models are PDE models. We will use different solution techniques for these different types of models, so it's important to be able to identify whether your model is algebraic, ODE, or PDE. Similarly, you should be able to look at model equations and determine whether the model equations are linear or nonlinear. When referring to linear and nonlinear, we're talking about whether the model is linear or nonlinear in the dependent variables and its derivatives. We also want to know whether the model equations are coupled or non-coupled, and whether they are explicit or implicit, because these characteristics will determine how we approach the model solution. Model solutions can be either analytical or numerical, and they can be exact or approximate. Analytical solutions to a full model are generally exact solutions. Numerical solutions can also be exact if we have error bounds and convergence criteria that define the uncertainties on our solution. Analytical solutions may also be approximate if we've made approximations to simplify the model equations. Remember that exact in this case doesn't mean that it exactly represents the real system that the model is describing. It only refers to the relationship between the solution and the model. Model solutions can be written in dimensional form or dimensionless form. Generally, dimensionless solutions are more generally applicable. Model solutions can be impossible, very difficult, moderately difficult, easy, or trivial to find. We will learn techniques in this class that make the impossible possible. That's what makes being a competent engineer so much fun. You're like a superhero. If this class teaches you how to take the impossible and make it possible, then I've given you a superpower.